This is like tubing tables. Let's have a small discussion on TPR. Discussion on TPR. Okay. That, if you remember, is tubing performance relationship. Okay. And the first thing is the tubing tables. So commercial software are typically used in commercial software. Okay. So what does it represent? So how do we put it? So the thing is that, let's maybe rearrange this. Okay, so in commercial software, instead of running delta P calculations along the tubing each time, okay, each time is needed. Okay, for example, can be flow equilibrium calculation, okay. Instead of, in our case, it will be that tubing equation, right? We called it every time, but instead of using it any time, okay, in commercial software, instead of running DP calculations along the tubing each time is needed, tubing tables, something called tubing tables, are used instead. And this means that the delta P at the tubing is pre-computed for many operational conditions, okay? For many operational conditions. Okay? And later, interpolation is made on the table. Okay? Instead of running the model live. Almost every simulator works in that way. So you remember we had our equation, right? That was the tubing PWH is equal to PWF squared. No, let's make it a different way. E to the S minus PWH squared 0.5, and here we have Q, right? Okay. Instead of using that equation every time I say I need delta P, I will use that equation. I pre-compute that equation on a table, okay, on what I call a tubing table. So what is the tubing table telling you? So if you had, let's say PWF, right? We have one situation, we have one well bore, one well. Okay, and we have here PWH and PWF. Okay, and we have certain Q. Okay. So what I do, I pre-compute with a range of Q and a range of PWF those curves. Okay, and if you remember, they are going to give you something like that, right? This is for a fixed PWH 1, okay? And you know from that equation it gives you that. So I compute those points, okay? Then for another wellhead pressure, P wellhead 2, what happens if I reduce the wellhead pressure? Will the curve be above that or below that? Remember, that curve is the pressure available or required, right, at the bottom of the tubing. If I fix this pressure is fixed, and therefore, if I have no flow, simply will be the hydrostatic, right? Okay. But if I start increasing, then the pressure has to be higher than the hydrostatic to flow against that pressure, right? And it becomes higher and higher and higher. That clear? I know I'm pushing it a bit now for the time, but just bear with me, okay? This pressure is fixed, 0 rate, it will be hydrostatic only, and then I start to increase, and then more and more friction losses, okay? Now what happens if that pressure, I lower that pressure? Let's say before it was 30 bar and now it's 20 bar. How will the curve look like?
It will go down.
Everybody agrees? Yeah? Okay. If I use PWH2, right, where PWH2 is less than PWH1, then I will have a curve that looks maybe like that. Okay, and then I have this curve here. Okay, and if I increase it, okay, the opposite. If I increase it, PWH3, okay, that will be for PWH3. Okay, and here PWH3 okay. So I make computations of all of these points I see there, okay, with that equation. That for gas is simply this equation, but for when we have other cases, for example, oil, we have gas with condensate, this equation doesn't hold, okay, so you need another procedure that we will discuss later. But you use that equation and you start from 0 all the way to a very high, to a Q max, okay. You subdivide in intervals, okay, so you say PWH equal to PWH1, okay, that will be one table, and then you say the rate here Q1, Q2, Q3, these are all of these Q1, Q2, Q3, Q4, Q5, and then I calculate here the PWF required that I need at the bottom of the tubing. PWF 1, PWF 1, sorry, that will be for other wellhead pressure. Make it nicer. Okay, for wellhead pressure 1, for wellhead pressure 2, for wellhead pressure 3, and so forth. PWF 1, 2, and so forth. So I go and I run with my model all of these possible combinations. So that's what I call, this table here is what I call my tubing table. Okay, this part here. Interpolating here is much faster than running the model. Okay, simply I just interpolate for any rate that I have. I interpolate and I find the PWF. Okay, so the justification is that interpolation in this table, on this table, is much more computationally efficient than using the equation. The equation, and it's simply dry gas is an equation or a method that simply tells me delta P as a function of Q PWH. Okay. Something. So how will you use that table now, I ask you, to find flow equilibrium? Okay, you have IPR, okay, PWF, and Q, and also actually Prosper also used a series of points for the IPR. So this guy, let's change the color, and with that we close our session. Okay, this color is the IPR. I have a series of points where I have interpolation. Okay. Okay. And how do I find now the equilibrium for PWH equal, for example, PWH1? Okay. So then I come, I overlap this other curve that I have. Okay. So from the table, let's make it, sorry, let's make a bit longer, even if it takes longer time. So your task is to find equilibrium for PWH equal to PWH1. Okay, so that's your task. Okay. So then you go to tubing table and extract the column PWH equal to PWH1. Okay, in my case I just go to that table that I have pre-computed and I hope that number is there. Okay, so I just take that column, okay, and impose on the plot, okay, and that will give me this curve. Okay, and then I simply find that intersection by interpolation. Okay, okay, so this will be PWF1 from the IPR. This will be PWF2 from the IPR. Okay, and this will be PWF1 from the TPR, and this will be PWF2 from the TPR. Okay, I see where I have a change in sign. Okay, and then I come and say, so how do I find that intersection? Okay, I have to make a point here, which is the intersection PWF star for a Q star, and here I have Q1 and here I have Q2, right? So I have to say the first equation is PWF1 from IPR minus PWF2 from IPR divided by Q1 minus Q2 will be equal to PWF1 IPR minus Q star. Okay, so I have one equation with two unknowns, and I have the second equation is the PWF from TPR 1 from the TPR minus PWF2 from the TPR divided by Q1 minus Q2. Okay, that will be PWF1 from the TPR minus PWF star divided by Q1. Okay, so two system of equations with two unknowns, I can solve it very efficiently.